Welcome. If you're gearing up for your board exams, you already know electric current is a huge topic. Today, we're going to break down the force that literally powers our world, from your phone right down to a simple light bulb. So let's jump right in.
All right, let's kick things off with a really fundamental question. I mean, you use batteries every single day, right? But have you ever stopped to think about what's actually happening inside? What's the real push that forces those electrons to start moving in the first place? Well, that's exactly what we're going to figure out. So here's our game plan. We're going to start right inside the battery with something called EMF. Then we'll see how to measure things in a real circuit. After that, we'll explore Ohm's law through a classic experiment, see what materials follow the law and which don't, and really dig into what resistance is. We'll wrap it all up with some key strategies to help you absolutely crush it on your exams.
Okay, let's get into our first section. To answer that big question about the push, we have to go deep inside the battery, down to the chemical level. That push we're looking for, well, it has a special name, Electromotive Force, or EMF for short.
Now here's the first thing you absolutely need to get for your exams. The name electromotive force is a little misleading because it's not really a force like gravity. It's actually the amount of work done for each little bit of charge. Basically, a chemical reaction inside the battery does all the heavy lifting, moving charges from the negative side to the positive side, and that's what creates the stored energy.
And the formula for this is pretty straightforward. E equals W divided by Q. Here, E stands for the EMF. W is the work done by that chemical reaction, and Q is the amount of charge being moved. So you see, EMF is all about the energy you get per unit of charge.
Which brings us right to its unit, the volt. So when you see a battery that says 1.5 volts, what does that actually mean? It means the chemicals inside are doing 1.5 joules of work for every single coulomb of charge that they move. EMF is just energy per charge. Simple as that.
Okay, and this is a big one, so listen up. A super common mistake is mixing up EMF and potential difference. They are not the same thing. The easiest way to remember it is this. EMF is the cause. It's the engine of the battery, doing the work. Potential difference, that's the effect. It's the result of that work that we can actually go and measure in a circuit. Cause and effect. Got it?
All right, so we've got the theory down, but how do we actually measure this stuff in a real circuit? Getting this right is so important, not just for your exams, but for any practical lab work you do. And this is absolutely crucial, a non-negotiable. A voltmeter, you always connect it in parallel or across a component. Why? Because it's built to measure the energy difference between two separate points. An ammeter, on the other hand, has to be connected in series or in line with the circuit, because its job is to measure the total current flowing through it. If you mix these up, you're just throwing away marks on your exam.
Now let's travel back in time a bit. Let's step into the lab of George Simon Ohm. He used a pretty simple setup to discover one of the most important laws in all of electricity. Let's retrace his steps and see what he found.
The experiment itself is surprisingly simple. You just take a conductor, like an iron spoke, and connect it to one battery cell. Then you grab your meters and measure the voltage and the current. But here's the clever part. You then do it again, but this time with 2 battery cells, then 3, then 4, systematically cranking up the voltage and recording the new readings each and every time.
Now when Ohm looked at his data table, he noticed something amazing. I mean, sure, when he added more batteries and the voltage went up, the current went up too. That makes sense. But the real breakthrough was when he calculated the ratio of voltage to current, V divided by I. For every single measurement, that ratio stayed exactly the same. It was constant. That was the big discovery.
And this incredible observation is what we now call Ohm's law. It states that the potential difference is directly proportional to the current. But, and this is a huge but, you have to pay close attention to that last little phrase, provided its temperature and other physical conditions remain unchanged. That condition is the key to everything, and we'll see why in just a minute.
So, in mass terms, we can turn that proportionality, V is proportional to I, into a full-blown equation just by adding a constant. And that constant of proportionality, well, we give it the letter R, and we call it resistance. And that gives us probably the most famous equation in all of electronics. V equals IR.
So this leads to a really important question. Does everything in the universe follow Ohm's law? Well, the answer is a big, fat no. And because of that, we can actually sort all materials into 2 main categories.
The easiest way to see the difference is to just graph it. If you plot voltage versus current for a material that obeys Ohm's law, we call those ohmic conductors, you get this perfect, beautiful straight line right through the origin. The slope is constant. But for something that doesn't obey the law, like an LED, the graph is a curve. That tells you right away that the relationship isn't so simple.
So let's just boil it down. Ohmic materials, like your typical metals, follow the rule and have a constant resistance. Non-ohmic materials, things like LEDs, semiconductors, even gases, they're the rule breakers. The resistance actually changes depending on how much voltage you put across them.
We've been talking a lot about resistance, and we know it's the ratio of V to I. But what is it, really? Like, on a microscopic level, why do wires get in the way of electricity at all? Let's zoom way in, down to the atomic scale.
Okay, picture an electron trying to zip through a copper wire. It's not some wide-open superhighway. No way. The path is totally crowded with this fixed grid of positive ions. So as our little electron tries to move, it's constantly bumping and crashing into these ions, losing some of its energy with every collision. That constant obstruction is what we call resistance. And all that energy it loses, that's what makes the wire heat up.
All right, we've built a really solid foundation of the concepts. Now let's get practical. How do we turn all this knowledge into actual marks on your exam paper? This is where we focus on the stuff that examiners really love to ask about.
First things first, you have to know the limits of Ohm's law. This is a classic exam question. Remember, it is not some universal law of the cosmos. It only really works for metal conductors and only when their temperature stays the same. It does not apply to things like semiconductors or liquids or gases.
Okay, here's another great one that really tests if you understand the concepts, not just the formulas. What is it that actually causes an electric shock? Is it the crazy high voltage or is it the current? Just take a second and think about it.
The answer is the current. Now think about it like this. Voltage is just the push. The push itself doesn't hurt you, but a really high voltage is dangerous because it has the power to push a large, damaging amount of current, the actual flow of charge through your body. It's the flow itself that does the harm.
And finally, let me give you a powerful exam technique. This is gold. For any question that asks you to define a law, especially if it's worth 3 marks, just use this 3-part structure. 1. State the law nice and clear. 2. Write down the formula and make sure you explain what each of the variables means. And 3. The part that so many people forget. Add the critical condition. For Ohm's law, that's at constant temperature. This simple framework pretty much guarantees you're hitting every single point the examiner's looking for. Use this and you are going to be in great shape.